Hello, hello, hello. This is Nicholas on this lovely Friday afternoon wanting to do a video that I've been really excited to make on the general Stokes theorem over manifolds. And this is an extremely marvelous theorem because it basically, all of calculus is a consequence of this one simple theorem. And this one simple theorem actually changes the way that you think about derivatives and integrals. So what is it saying first? Very loosely speaking, the way to think about it is that the total change on the outside is the sum of the little changes on the inside. Now I'm going to elaborate on what that means in just a second, but let's just define some notation here. We're saying that the integral over the boundary of m here being a manifold, so a manifold being a topological construction that is locally Euclidean but not necessarily globally. In the case of this video, though, you can just think of this manifold as being this sufficiently nice continuous space. In 1D it could be like some sort of line or curve. In 2D it could be a plane, or in 3D it could be some sort of surface, like a paraboloid would be considered a manifold. And then this omega here, and so also m is over the manifold. Del m, this Greek letter delta or del, is the boundary of the manifold. So in the case of 1D, the boundary would just be the two endpoints. Or in the case of 2D, the boundary would be a 1D line, and so on. Now, omega is, if m is a what we call a K-form. So a K-form, in this video, I'm going to be proving various vector calculus theorems that go up to 3 dimensions. So let's just deal with K-forms in up to 3 dimensions. Now, what is a K-form? Okay. A K-form, so if we're dealing in R3, the definition of a K-form, if we let K be equal to 0, we just end up getting a particular function, f of x, y, z. That would be a 0 form in R3. Just any 3D or any scalar function with 3 inputs and 1 output. Now, a 1 form in R3 would be where we have a function still of 3 input variables. I guess I'll write it out in this case. P of x, y, z dx plus q of x, y, z dy plus r of x, y, z dz. Now, we call it a 1 form, I guess, because it's got one differential that comprise the 3 axes in your space attached to the functions. And it doesn't have to be 3, it doesn't have to be x, y, z, it could be x1 to xn. I'm just dealing in R3 because that's what I'm going to use for later theorems. Now, a 2 form would be, still we would have p, q, and r, except now it's all possible ways to attach 2 differentials to them. So we would have p dy dz plus q dx dz plus r dx dy. This is just the form of a 2 form in R3. And then lastly, a 3 form in R3 would look like, now it's all possible ways that we can take these 3 differentials, dx, dy, dz, and attach them to a function. Well, there's only one way to attach 3 differentials if we're doing them 3 at a time. That's just dx, dy, dz, and then we would have them attached to a function, say, f. So this is the forms that we're going to be dealing with, and it gets much more general than this. But just for the sake of this video, this is what we'll be sticking to for K-forms. So omega, then, if M is a manifold, which we'll call a K-form, we'll define that to be a k form. Then we let omega be a k minus 1 form. Okay, hopefully you could stick with me there. Now, let's go back to this here. The total change on the outside is the sum of the little changes on the inside. Now, let's look at, just to see how powerful this theorem is, let's look at the baby case of the fundamental theorem of calculus, okay? Now, and just kind of looking at these words, let's come up with it in terms of the kind of simplified version of general Stokes theorem. The total change on the outside, so if we are integrating over this 1D line segment from A to B, the total change on the outside is f of B minus f of A. In this case, we could think of the fundamental theorem of calculus as the zero form version, as letting omega be a zero form of the general Stokes theorem. So the total change on the outside is f of B minus f of A. The sum of the little changes on the inside, well, the sum becomes the integral, and it's over the inside, so it's over A to B of f. And that's the fundamental theorem of calculus right there. Now, if we're thinking about this more in the language of Stokes' theorem, what we would say then is that we'd be considering a zero form in R1. So when we have a zero form in R1, applying Stokes' theorem, the boundary of the manifold is just the endpoints, right? Because we're dealing in this line segment here. So that's the integral from A to B of this zero form in R1. Now the zero form in R3 was f of x, y, z. The zero form in R1 is just f of x dx is equal to now the integral over that whole region of the derivative of our zero form, which I'll just call df. And now one thing I'd like you to notice is that, and these are of course both equivalent statements of Stokes' theorem, is that what's really happening here is that the integral is still there, right? The integral, and in general, the integral doesn't really go away. It's like when we're taught fundamental theorem of calculus in a Calc 1 or Calc 2 class, we think of the derivative and the integral as being the opposite of one another. But this is really only the case when we have a zero form in R1. In general, the integral and the derivative are not the opposites of one another. What has changed from Stokes' theorem on the left side and on the right side? We still have an integral, but the thing that's changing is we have the boundary of our manifold and our k minus 1 form and the derivative of our k minus 1 form. In other words, we have the boundary and the surface, the manifold, and the k minus 1 form and the derivative of the k minus 1 form. What this is telling you, this is really a profound result and interpretation of the derivative. It's not that the derivative and the integral are opposites of one another. It's that the derivative and the boundary are opposites of one another. And this is really a tremendous result. It motivates, and what we're now going to do is prove two very common vector calc theorems using this interpretation of Stokes' theorem. And they really all fall under that belt of just taking the integral of something over its boundary is the integral of something else over that surface of the derivative of whatever. So let's look at the case of Green's theorem. So Green's theorem. Now I'm not going to go through all the necessary conditions for Green's theorem to hold, but let's just assume that we're working with a vector field that's sufficiently nice. Okay, so Green's theorem says, typically the way you'll see it stated is that the line integral over a curve C of p dx plus q dy is equal to the double integral. So if C is the boundary of the region D, then we're taking a double integral over that whole region D of the partial of q with respect to x minus the partial of p with respect to y dx dy. Or this is sometimes written as dA, but you do have to pay attention to the sign, and I'll explain that in a minute. And P and Q are vector fields. They're the components of the vector field F. So F would be a vector field. F would be a vector field, and its components would be given by these two scalar functions, P of xy and Q of xy. Okay, now let's see how this lines up with the general Stokes theorem. So, Green's theorem deals in the case where we're in 2 dimensions. We're in R2. That's what the domain of our integral is. It's a region in R2, and it's a one-form manifold. Naturally, because we start with one line integral. So what's the form of a one-form manifold? Well, omega then, our one-form manifold, would be P of xy dx plus Q of xy dy. Okay, so realize that, wow, okay, that's very similar. It's actually exactly what we have on the left-hand side. We're halfway done. Okay, now d omega is, I'll write it for now as just dp dx plus dq dy. Now, dp is the total differential of p. We need to use the multivariable chain rule here. So d omega is the partial of p with respect to x dx plus the partial of p with respect to y dy dx. Now, what did I do there? I just replaced dp with the total. Dp is the total differential. This is the definition of the total differential. Plus the partial of q with respect to x dx. Plus the partial of q with respect to x dx plus the partial of q with respect to y dy dx. Now at this particular point, I do have to introduce some new notation here. And what I'm going to just give a brief overview of is the wedge product. Basically, the wedge product is a notation from exterior algebra that more formally denotes and more generally denotes multiplication of differentials. If we have just dx dy, we write that in wedge product notation as dx wedge dy. Another important property of the wedge product, like the cross product, is that it's anti-commutative. In other words, dx dy becomes, you could write it as -1 times dy wedged dx. And lastly, and this is kind of a pretty common result, we define in the wedge product the multiplication of two differentials at least 2 or more times to just go to 0. So in other words, dx dx or dx wedge dx goes to 0. And typically you'll see that in a lot of like physics proofs and also in some calculus proofs, where if you're taking if you've got dx multiplied by itself like 2 or more times, you take it to 0. Okay. Now using this notation, let's just stick in the wedges here. So wedge dx, and I realized that I accidentally wrote dx here. I meant to write dy. My bad. So let's just use the properties of the wedge product now. Realize that any differential wedged with itself is 0. So this goes away, and this goes away, because we're going to have a dy wedged with a dy. The wedge product is distributive, though, so what we're going to end up getting then would be the partial of p with respect to y dy wedge dx plus the partial of q with respect to x dx wedge dy. And now we just need to be careful here because we have dy wedge dx and dx wedge dy. And since the wedge product is anti-commutative, we just have to deal with the signs here. Usually it's nice to take it in alphabetical order of x and then y. So I'll instead write this as the partial of q with respect to x minus the partial of p with respect to y dx dy. And voila, that is exactly what we have on the right-hand side of Green's theorem. And we're done. That's a super simple proof of Green's theorem as the general consequence of Stokes' theorem. And now you could write it also as the negative of the integral over d of partial of p with respect to y minus partial of q with respect to x. And then in that case, you'd be integrating dy dx. Or I already flipped the order, so I don't need to put that negative sign. But in other words, if you want to change the bounds from, if you want to change the order in which you integrate from x to y, you want to make it y to x instead, just flip-flop the sign, which is just a consequence of the wedge product being anti-commutative. Okay, I would like to do one more vector calculus theorem, the Gauss's divergence theorem. Okay, so Gauss's divergence theorem deals with a two-form manifold in R3, just like how in Green's theorem, R3, we had a one-form manifold in R2. So applying the definition or applying Stokes' theorem with those conditions gives us that we have a surface integral. So the surface, which is the boundary of our region, which I'll call E, of omega, is equal to the triple integral over our region E of d omega. And again, omega is our two-form manifold. So, what is the form of a two-form manifold? Well, omega is, and realize that all my functions here are in R3, so it's of x, y, z, but I just don't want to write of x, y, z every time. So we're going to have p dy dz plus q dx dz plus r dx dy. And this is really p of x, y, z, you know, and so on. Okay. Now, d omega is dp dy dz plus dq dx dz plus dr dx dy. Okay, let's just replace the total differential with its definition. This is going to get a little yucky, but not too bad. So, we have the partial of p with respect to x dx plus the partial of p with respect to y dy plus the partial of p with respect to z dz dy dz plus the partial of q with respect to x dx plus the partial of q with respect to y dy plus the partial of q with respect to z dz dx dz plus the partial of r with respect to x dx plus the partial of r with respect to y dy plus the partial of r with respect to z dz dx dy. Okay, that's d omega. Now, using wedge product notation, we'll write these differentials using wedges, dy dz, wedge dx, wedge dz, wedge dx wedge dy. And now it's just a matter of applying the properties of the wedge product again. Okay, this is ultimately going to go away. This is ultimately going to go away because we're wedging it with a dy and a dz. This is going to go away, that's going to go away, and that's going to go away. And so we're going to end up getting, let's see, partial p with respect to x plus partial q with respect to y plus partial r with respect to z times each one of those terms has a dx, dy, dz. Oh, wait a second. Okay. That is nothing but what we define as the gradient pseudovector dotted with our vector field f dv, right? Where the gradient pseudovector is, it's really an operator. It's the partial with respect to x, partial with respect to y, partial with respect to z. It's just for a convenience of notation. But what is the gradient dotted with the vector field f? That's just the divergence of f dv, which is exactly what we have on the right-hand side of the divergence theorem, right? Now, on the left-hand side, we have an f dot ds. So we established the right-hand side is the triple integral over the region E of the divergence of f dv. That's equal to a double integral over the boundary of E, in other words, the surface integral of f ds. Now, f we just defined as our vector field, p of, I'll just, it's of x, y, z, so p, q, r. F is our vector field, and then ds is essentially for this video, what you just need to know is that df is just what's going to give us this dy, dz, dx, dz, and dx, dy. In other words, applying the definition of the dot product, ds would ultimately become dy, dz, dx, dz, dx, dy. And that proves the divergence theorem. So ultimately, what I'd like you to take away from this video is, one, just how beautiful the general Stokes theorem is that that it's a consequence of all of calculus. I mean, all of calculus is a consequence. And look at how simple it is to write down. I could just go on and on about it. But also another thing I'd really like you to take away from it is the interpretation of the derivative. That being that the derivative and the integral, that being that the derivative and the boundary are what are opposites of one another, not the derivative and the integral. And I think with that, we're done.